Next we have exercise 18. In this one, F is a field of characteristic 0 and A is a matrix in our matrix algebra Fn which has trace 0. Then we have to prove that there exist matrices B and C in Fn such that A equals BC minus CB. So let's solve this. Let us start the solution like this. Let us collect all matrices of this form BC minus CB and call that collection Kn. We write the suffix n here to emphasize that we are dealing with n by n matrices because we are going to change n. Although n is fixed here, but we are going to eventually apply a kind of induction in which we will have to change n, that is why. Alright. Now let u and v be two elements in Fn and let us consider the matrix W which is uv minus vu. This means that W is in Kn, and then using W we are going to define another matrix X like this. So what you see here are blocks in the matrix X. One block is W. This is a single field element which of course is 0, and this A is a row and B is a column. So this row and column are of appropriate sizes so that this X becomes an n plus 1 by n plus 1 matrix. That means W is already an n by n matrix because W is uv minus vu, which themselves, u and v are themselves n by n matrices. So we are increasing the number of rows by 1 and the number of columns by 1 to create X. This A actually itself can be a row of any entries. Similarly, B also is a column of any entries. Now the claim is that this X belongs to Kn plus 1. So X will also be a matrix which is like this. Say CD minus DC, where both C and D are matrices not in Fn but in Fn plus 1. So let us prove this claim first. Now before we prove the claim, let us make the situation even more convenient for us. Let's see how. Say alpha is any scalar coming from F and we consider the matrix U plus alpha 1. Here 1 is the n by n identity matrix. In place of 1 you can also write capital I if you want. If you feel this will confuse you, you can also write capital I. Now if this matrix is not invertible, then by the definition of characteristic roots, minus alpha is the characteristic root of the matrix U. Alright. So if you now keep changing alpha and you keep getting non-invertible matrices U plus alpha I, all those minus alphas are going to be characteristic roots of U. But of course you cannot just keep getting different characteristic roots without any bound. And that is because U only has finitely many characteristic roots by theorem 622. There is one more thing. Because the field has characteristic 0, it is in particular infinite. So if you have by chance chosen those alphas for which U plus alpha I are not invertible. So that way you have got as many characteristic roots of U as you can possibly get. But the field doesn't run out of elements because it is infinite. So you can choose at least one beta in F for which U plus beta 1 will be invertible, so that minus beta is no longer a characteristic root of U. Alright. Now you go back to W. What was W? W was uv minus vu. Now in place of U, if I write U plus beta I, what will happen if you do this multiplication using the distributive laws that we have in the matrix algebra? you will get uv minus vu. Along with these things, you also get beta times 1 times v. 1 times v is v. So from here you are getting beta v, and from this product also you are getting beta v. Recall that in an algebra there is that one axiom also, that last axiom, which allows you to write in place of v times beta 1, beta times v1. So that is also beta v. So this beta v and minus beta v cancel out, and you are left with only uv minus vu, which is our original w. This shows that if you can express w in this form, then you can also express w in this form, where the first matrix is an invertible matrix. So we can assume without loss of generality that u itself is invertible. If it is not originally, then you are considering one such matrix. Let us call that u itself. And now we will start our calculation. Let us now look at this block matrices. This one is, you understand that here the block pattern is exactly like the original X. In this corner you have U, which is an n by n matrix. U is our U, original U. This 0 is a single field element. Is the single field element 0? This other 0 is a 0 row of necessary size, and this 0 is a 0 column of necessary size. So that this is now entirely an n plus 1 by n plus 1 matrix. Similarly, we also have this other block matrix, where this one is V, this 0 is single field element 0. This one is minus A times U inverse. Note that we can write U inverse because according to our assumption, U is invertible now. And this one is U inverse V, U inverse B. I said V, sorry, slip of tongue. U inverse B. So now what we are looking at is this matrix times this matrix minus this matrix times this matrix. Now let us do the multiplication and see what we get. The multiplication, when you do this type of multiplication of matrices which are in block form of the same block pattern, then it's like you are treating the individual blocks as elements, okay, as if their elements are entries in the matrix, and you do ordinary multiplication. Keeping in mind, of course, that whenever you multiply two blocks, there you are actually doing multiplication of matrices when you multiply two blocks. For example, what will be the entry here in this position? It will be 0 times 0 plus 0 times this. So when you are doing 0 times 0, you are actually just multiplying the field element 0 with itself. So that's a single element. Plus this 0 times this 0 is a 0 row, and this is a column. Okay, so that way you have to interpret this other product, which ultimately will give you 0, but I am just simply saying how this multiplication goes. So this times this plus this times this ultimately is 0. Next, how does this entry come? This entry means actually it's a row. It is this times this plus this times this, again 0. You do not have to worry too much about the fact that this multiplication actually really goes well. There is no problem, it goes well, okay. You just simply treat these entries as if they are just ordinary entries, and you do the multiplication. So for the next row, this times this plus this times this, okay. Now you have to be careful. What is U inverse B? Actually the product is U times U inverse B, but because matrix multiplication is associative, you can consider U and U inverse together. That gives you the identity matrix. that times B is B itself. So that way you get B here. And finally, this times this plus U times V is UV. Okay. Minus. What about this product? This times this plus this times this is 0. This times this plus this times this will be U inverse, and U will give you the identity matrix. Minus A times the identity matrix is minus A. Again, do not forget that minus A actually is a row. But anyway, you get minus A. Next, this times this plus this times this is 0. And finally, this times 0 plus V times U is VU. And then when you do the subtraction, what do you get? 0 minus 0 is 0, of course. 0 minus minus A is plus A. You do understand the meaning of this minus A, right? Here, all the entries of the row A are, in place of those entries, you are writing their additive inverses. That's what it means. So minus of that becomes A. B minus 0 is B, and here you have UV minus VU. So UV minus VU is W, and this is your X. So you actually have been able to express X as, say, let me call it C and this D. CD minus DC, where C and D are both n plus 1 by n plus 1 matrices. And that's how X really belongs to Kn plus 1. So our claim is established. Now what are we going to do with this claim? Let's see. So now we are going to prove our actual result, what we have been asked in the exercise. And we are going to apply induction on n to prove that result. Let us first consider the base case where n is equal to 1. What can we say about the matrix A in this case? A is a 1 by 1 matrix whose trace is 0. Since trace is the sum of the diagonal entries, so the only element here, which itself is a diagonal entry, has to be 0. But then A can be expressed like this: 1 times 1 minus 1 times 1. Think of the first one as B and the second one as C here. So that way A has been written in the form BC minus CB, which means that the claim is true here trivially. So that is the base case of our induction. Next, let us consider the induction hypothesis. Let the claim be true for some positive integer n. And then for the induction step, let us consider a matrix A, this time in Fn plus 1. So A is now an n plus 1 by n plus 1 matrix which has trace 0. And at this point, we have to take the help of the previous exercise, which being an odd numbered exercise, we haven't solved it. But whatever we did in the first part of the solution, you can use that to try to solve this one. But anyway, let's see what it says. By exercise 17, because F is not changing, F is always there, F has characteristic 0, and we are dealing with a matrix of trace 0. So this exercise says that then there exists an invertible matrix C of the same size as A, such that CAC inverse has only zeros on its leading diagonal, on its main diagonal. So we have this. Let us first use this information that all the entries on the leading diagonal of CAC inverse is equal to are equal to 0. To write CAC inverse in this block form, if all the diagonal entries are 0, in particular the first diagonal entry will also be 0. So we separate that as a single block, and along with that you already know the pattern. This W is a submatrix of size n. It's an n by n matrix. That's why we have written where W belongs to Fn. And A and B are respectively rows and columns of appropriate sizes. Now it is given that A has trace 0, but we know from our previous study of the trace function that the trace of CSE inverse is actually equal to the trace of A. So that is also 0. That means this matrix has trace 0. But what is its trace? That is the sum of all the diagonal elements. So from the way W is appearing here, you can clearly see that the trace of A is equal to 0 plus the trace of W. So that is why the trace of W is also going to be equal to 0. Well, actually you can just simply note this fact that all the diagonal entries are 0. So from there also you can get the fact that trace of W is going to be 0. But anyway, W now is a trace 0 matrix in Fn. So our induction hypothesis is applicable on W, that is W now belongs to Kn. And then we have this CSE inverse belongs to Kn plus 1 by the first part of the solution, because not this form. This form is just like how we had x back there, and we proved that if W is in Kn, then x is in Kn plus 1. So that's why now CSE inverse is in Kn plus 1. But by the definition of Kn plus 1, then CSE inverse will be of that form GH minus HG for some matrices H and G in Fn plus 1. But you have to express A in that form, not CSE inverse. You note one thing that you can here multiply both sides from the left by C inverse. So that way this C will vanish, and multiply both sides from the right by C. So that way this C inverse will vanish, and that will produce C inverse here and C here. Originally you had GH, now you will have C inverse GHC. But we have brought one extra C and C inverse, which anyway cancel out. So that way we get C inverse GC times C inverse HC. What happens to HG? Same. Previously it was HG, now it will be C inverse HGC. And this time here we have written again C and C inverse. So that way you see that A is of this form. Let me call this matrix X momentarily. X times Y minus Y times X. That's what we wanted to show. So our induction is complete and the result has been established. So that will be all for today. See you next week with more exercises and their solutions on the same day. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.